Hello, this video we will continue looking into second law of thermodynamics, and particularly we're going to looking at Clausius Statement, and we will be using refrigerator as example. Because last time we talking about Kelvin-Planck statement and we used the heat engine as example and to understand another aspect of second law. And so now let's first look at Clausius statement. What did it say? As usual, it's very abstract at the beginning to look at this. Again, I want you to be sure, and at the end of this video, you will have great understanding how this really mean through example we do on refrigerator. So it said it's impossible for any system to operate in a way that sole results would be an energy transfer by heat from cooling to hot. Well, let's just say a simple way. Heat transfer cannot happen from cold to hot, right? Naturally only go from hot to cold. So it defines the direction of the process. So in that situation, hot to cold, yes, and cold to hot, no. You cannot cook a steak by placing it in the fridge. The heat will not automatically taken from the refrigerator to transfer to the steak. Okay. So first what we're going to do is we're going to draw a schematic of refrigerator cycle. So we start with a hot reservoir, TH, and then we have our thermodynamic cycle, and this is going to be our refrigerator. Then come out, that's going to be our lower temperature reservoir, TL. Okay, so what does refrigerator do? It's pretty cold already in the fridge, right? You want to actually taking the heat from cooler to the hotter area. And in order to do that, we're going to have some kind of work coming in to do. So what's exactly happening inside this refrigerator that makes things happen, right? We're going to draw this. Start with a compressor. If you look at your refrigerator, there's always going to be a compressor motor at the bottom. So if we were trying to draw that first, that's going to be our compressor. And a compressor, you're going to have a work come in to compress and what's inside the compressor? Normally that's going to be your R134, your freon, as a gas form. So when it's being compressed, it's going to live over here. And when it's compressed, the pressure goes up, right? You're going to get a higher pressure. And we're going through this condenser coil. Okay, so we understand condensing is from gas to liquid, right? In order to change the phase from gas to liquid, you will release the heat. So there will be heat leaving out condenser. So where is condenser located in the refrigerator? It's normally at the back of the refrigerator, and they have this condensing coil. So what happens is when there's freon here, it's being compressed and it's at high pressure, and often it's getting really hot as well. And this temperature of the freon is so hot compared to the kitchen environment. It's even hotter than kitchen. So normally when you stand behind the refrigerator, you will feel like being soaked, being soaked in sauna, right? Because it's so hot, because that heat is transferred from this hot R134 to the kitchen. So there's a heat leaking out. In order to, once the heat is leaking out, what happened? This freon is going to change from gas to liquid. Okay. So what happens here, if we assume it's going to become out as saturated liquid form. So earlier here, you come in as gas form and being compressed at high pressure and then condensed to liquid. Then at this liquid, we're going through this throttling valve. That's going to be the symbol for throttling valve, like an hourglass. And if you need to review what throttling valve do, there's a video earlier on in open system talking about throttling valve, this restrictive tube, or we call capillary tube for the refrigerator. It has a porous plug or adjustable valve in the middle. It will restrict the flow, will reduce the pressure. However, the magic thing happens is when the freon is inside, accompanying to the pressure drop, the temperature dropped tremendously. There was an example at the earlier video to show how much temperature drop for passing the throttling device. So now thinking about this R134, this freon gonna pass this throttling valve, and then as a result, we pressure drop, right? So far, all those are high pressure here at the beginning, because during the condensing process, the pressure stayed the same, right? And the temperature stayed the same. It just changed from gas to liquid. And now here the pressure dropped from high pressure to low pressure. Then we also drop our temperature tremendously. Then what we are going to have, we're going to pass our last component we call evaporator. All right, so this is a coil that's located in the freezer section, okay? So that's evaporator coil. After throttling valve, there will be some part of it might be gas. So this, let's assume if it's a liquid vapor mixture. If it's a liquid vapor mixture, then they are going to go through this evaporation. What happened at evaporation process? This means our gas is gonna, our liquid is gonna change to gas, it's gonna evaporize, right? In order to do so, we have to add heat to it. There's gonna be heat come into the system. Okay. And where is that heat coming from? That's how refrigerator work. Okay. This freon passing through this evaporator coil, it's so cold. Let's say if it's a negative 30 degrees Celsius, okay? And then the normal refrigerator space temperature is about 1 degree Celsius, So in that situation, 1 degree is considered pretty cold already. However, freon is negative 30. So the heat transfer naturally going from hot to cold, from 1 degree to negative 30. So in that case, we achieve our purpose of refrigeration. We're going to continue get the heat coming from the refrigerator space to the cold freon. That's how the refrigeration works. So when the freon absorb this heat, that's when its gas becomes liquid, right? Okay, so gas become liquid, then they become a vapor again. So this vapor gonna come back going through this compressor being compressed. Okay, then this cycle restart again. All right, so let's do a quick recap of this refrigeration cycle. You start with our compressor, and you have this freon gas and being compressed. then you get to high pressure. At this high pressure, you have higher temperature, and this higher temperature is way too hotter than the kitchen. So you're gonna feel that heat coming out from this condensing coil because heat transfer from hot to cold. And because the heat is leaking out from Freon, right, is transferred from Freon to the kitchen, and the Freon is gonna release the heat, so going from gas to condensed to liquid. And then when this liquid passes through this throttling valve, the pressure drops so badly, and also this temperature drop a lot, right? When this temperature drops so much, and this temperature compared to the refrigerator space, you know, it's way too low. Therefore, the heat is transferred from, naturally again, from hot to cold. It's from the refrigerator space to this freezing cold Freon. Okay, to achieve the purpose of refrigeration. And then, since this Freon taking the heat coming to the system, and here I'm going to add a little note, it's going to be Q from lower temperature reservoir, and this kitchen right here is going to be our higher temperature reservoir, so I'm going to call QH. That means like related to the, this is TH, higher temperature reservoir. This is going to be our refrigerator space. That's going to be our TO. Okay, since this heat is taking out, is added in for the Freon, so it's changed from liquid to gas, and then starting this process again, compress it again. Okay, so that is our Clausius statement using refrigerator as an example. Now we're going to looking at efficiency. We're talking about in the last videos about the heat engine efficiency, and here we have abbreviation called the COP. That means coefficient of performance. This is used for refrigerator appliance. So if it's a COP add R means refrigerator. That's going to be again your desired output over required input. And what would be the desired output for this refrigeration cycle? What do we want? Look at all that. Do we want the work come in, or do we want to heat least out to the kitchen, or do we want the heat suck out from the refrigerator space? Of course, that would be Q in, right? We want more and more heat taking out from the refrigerator space. Q in, that's what we desired, or we can write it down as QL, which means it's from the lower temperature reservoir. And then what's required? What absolutely have to have? We're going to have this work in, right? Required work. So now we have a formula, our first formula for coefficient of performance for refrigerator. It's going to be QL over W required work, or QN over WN. Okay, now let's look at the cycle. Let's write a cycle conservation equation. By looking at this cartoon, we can see this entire cycle here. What's coming into the system? Coming into the system, we're going to go ahead and label now. So this is hot reservoir, that's our kitchen, right? And that's going to be Q out, would be this one. and we're going to call it or QH. That means higher temperature reservoir. And here we need to take out heat from lower temperature reservoir. We're talking about that's our refrigerator space. And that's going to be QA into the system. And that we call QL. That's the heat taking out from the lower temperature reservoir. So look at the cycle here. What coming into the system? That would be QL and work coming from compressor. Those two arrows goes into the cycle. And what comes out will be this, right? Will be this QH. That's going to be the heat going out to the kitchen. So knowing this, that's another important equation for refrigerator. Knowing that one, we can replace our COP, coefficient of performance of refrigerator, with QL is basically your QH. Actually, we're going to replace work in, okay? So QL stay the same. Work in is going to be equal to QH minus QL. So in other words, the heat going out of the kitchen minus the heat we desired going to taking out from the refrigerator space, that's going to be our work in. And so that's going to be our another expression for COP for refrigerator. That's it. So that's our discussion on Clausius statement using refrigerator as an example. And the key element to understand is knowing how those four components, the compressor, condenser, throttling valve, evaporator work together to achieve this purpose, and how we measure its efficiency. We are using desired output QL over required work WN, and knowing how the cycle conservation work. And then we have another expression for COP. That's all for this video. I'll see you next time. Bye now.